When you look up into that deep night sky, it feels infinite, doesn't it? Like the edge of everything.
Mm-hmm.
Vast.
But what if that starlight, that darkness, is just one page in a much larger story?
A story with hidden chapters.
Exactly. Chapters written in dimensions we can't see, realities tucked away, but maybe influencing everything.
It's a theme that runs deep, this idea. You see it woven through so much of the material you gathered. This sense that there's more to reality than meets the eye.
It's this incredible, persistent human dream, isn't it? To find that one single story, that theory of everything that ties it all together.
A cosmic Rosetta Stone, in a way, to translate the different languages the universe seems to speak.
And that's where we're drifting tonight. Into these whispers, these hints from mathematicians, physicists, people who've listened closely to the universe's mathematical heartbeat.
Following the clues they found.
Yeah. We'll explore these ideas of dimensions beyond our own. Think of it like a gentle journey for the mind, just before sleep. A journey driven by that search for ultimate unity. And that search really starts with looking at the fundamental players, the forces that shape everything.
Right. We see gravity holding us to the Earth, holding galaxies together.
Then there's electromagnetism, light, electricity, magnets, all that stuff.
And then the nuclear forces, the strong and the weak, working deep inside atoms.
They do seem quite different, don't they? Like siblings with very distinct personalities.
That's a great way to put it. Gravity, the sort of quiet, universal one, affects everything with mass.
While electromagnetism is pickier,
Yeah.
only cares about charged particles, an uncharged particle just floats right by.
And the strong force is even more exclusive.
Oh, yeah. It holds the protons and neutrons together in the nucleus, dealing with quarks. But it completely ignores electrons, neutrinos, the leptons.
And the weak force.
That one's involved in specific transformations like radioactivity. Very specialized.
They really don't seem like they belong together sometimes.
On the surface, maybe not, but the really powerful idea, the one that keeps physicists searching, is that they do belong together.
That they were once unified.
Exactly. Back in the very first moments after the Big Bang, unimaginably hot, incredibly dense. The idea is they were all just one single force then.
Like steam, water, and ice are all HO.
Precisely. Different states of the same underlying thing. As the universe cooled, this single force froze out into the different forces we see today.
And we've actually seen proof that this kind of unification can happen, right?
We have the unification of electromagnetism and the weak force, the electroweak force back in the 60s. That was huge.
A major piece of the puzzle clicked into place.
Mm-hmm. It showed it was possible. It fueled the dream of bringing the other's gravity and the strong force into the fold, too.
And this is where things get really strange, where the idea of extra dimensions comes in.
Yes. It wasn't like someone just tripped over a fourth spatial dimension. It emerged from the mathematics as a potential pathway to unification.
Kaluza and Klein. Their names pop up a lot here.
Pioneers. Theodore Kaluza, back in the 1920s, had this startling idea.
What if gravity and electromagnetism aren't separate?
What if they're just different views, different manifestations of a single force operating in 5 dimensions?
5. Our 3 space dimensions plus time and one more.
One more spatial dimension. In that 5D space, gravity and electromagnetism could potentially be described by a single unified set of equations. Our perception of them as separate would just be an artifact of us living in, well, fewer dimensions.
Wow. Okay. But where's this 5th dimension?
That's where Oscar Klein came in a bit later. He took Kaluza's idea and added a quantum twist.
He suggested it wasn't some infinite new direction.
No. He proposed it was curled up, like incredibly tightly wrapped in a tiny, tiny loop at every single point in our space.
So small we can't detect it.
Far too small.
Oh.
He even estimated its size, linking it to things like Planck's constant. It's almost poetic. A hitting circle everywhere and nowhere, holding a key to unification.
It resonates with those really old ideas, doesn't it? That what we see isn't the whole picture.
Absolutely. Plato's cave comes to mind immediately. The prisoners seeing only shadows.
And thinking the shadows are reality.
Right. Or wayang kulit, the Indonesian shadow puppets. Complex stories told by figures we don't see directly, just their projections. Our reality might be a projection from somewhere deeper.
Our whole understanding of space has changed so much over time, too.
Oh, definitely. Thinking the Earth was flat, with a dome over it.
Seems so limited now. Then the Renaissance, figuring out perspective in art, making 2D look 3D.
And the explorers proving the Earth was round, a huge shift.
And Galileo, turning his telescope up and seeing mountains on the moon, moons around Jupiter. Suddenly, Earth wasn't the center of everything. It was just a place.
A place among other places. A profound decentering.
And while all that was happening with our view of physical space, mathematicians were exploring abstract space, higher dimensions.
They were. It really kicked off with challenging Euclid, that famous parallel postulate.
The one about parallel lines never meeting seemed obvious, but
But could it be proven from the other axioms? For centuries, no one could. Until Gauss, Bolyai, Lobachevsky, they realized independently that you could build perfectly consistent geometries where it wasn't true.
non-Euclidean geometry, where parallel lines can meet or diverge infinitely.
Exactly. Suddenly, geometry wasn't just about describing our space. It was about exploring possible spaces, wild, abstract landscapes.
Like that story of the woodcutter's son lost in a non-Euclidean forest. Infinite parallel paths. Mind-bending.
It really captures the strangeness. And then came Riemann.
He gave a framework for all of this. For hyperspace.
He did. He generalized the whole concept of geometry. He introduced the idea of the metric.
Which is like a ruler for any kind of space.
Sort of. It's a generalized Pythagorean theorem, basically. A rule for measuring distance between points. And crucially, this rule could change from place to place, allowing for curved space, warped space, in any number of dimensions.
So space didn't have to be flat Euclidean space anymore.
Not at all.
Yeah.
And he talked about curvature in higher dimensions, how to understand the shape of these spaces, maybe by imagining them embedded in even higher dimensions, like picturing a hypersphere within 4 dimensions.
It feels like peeling an onion, but the onion is reality itself.
It does. And others, like Cayley and Grassman, pushed this mathematical exploration further. Cayley had a simple definition. Dimension is just the number of coordinates you need to pinpoint something.
3 for space, add time makes 4. Simple but powerful.
And then there's Mobius, looking at left and right-handedness, chirality.
Like our hands or shoes,
Mm.
mirror images, but you can't turn one into the other in 3D space.
Right. Mobius realized you'd need to flip through a 4th dimension to do that continuously.
Ah, the Mobius strip. That's related, isn't it? The loop with only one side.
Exactly. It's a 2D object that, if you trace it, flips your orientation. A little chirality changer in 2 dimensions.
And the 3D version is weirder.
Much weirder. The Klein bottle. A bottle where the inside connects to the outside without a hole. Impossible in 3D, but conceivable in 4D. These aren't just math games. They hint at what higher dimensions could allow.
It's amazing how imagination, pure math, can explore these possibilities. And then there's Flatland. We have to talk about Flatland.
Edwin Abbott's masterpiece. Such a clever way to build intuition.
A whole world of 2D shapes. Squares, triangles, lines, living on a flat plane.
And our hero, a square, encounters a sphere from the 3rd dimension.
Which just appears as a circle that changes size as the sphere passes through Flatland. Completely baffling to the square.
It perfectly illustrates our own potential limitations, doesn't it? How could we perceive a 4th dimension intersecting our world?
Abbott hoped it would make people aspire yet higher, to think about 4D, 5D.
A beautiful invitation to expand our minds.
And these ideas didn't just stay in math and fiction. They started having physical implications.
Yes. Paul Ehrenfest asked a crucial question. Why three spatial dimensions? Does it matter?
And does it?
It seems to matter profoundly. Ehrenfest's work suggested that stable planetary orbits, like the ones in our solar system, are only really possible in three spatial dimensions.
Really? What happens in other dimensions?
In more dimensions, gravity would likely be too strong, pulling planets into their stars, or too weak, letting them drift away. Stable atoms might also be impossible. It suggests our three dimensions might be special, necessary for things to be stable, for life, perhaps.
Wow. That grounds it in a very real way.
Ah,
So our 3D existence might be finely tuned.
it's a compelling thought.
Okay, let's loop back to Kaluza. You mentioned flat land might have inspired him.
The story goes he was thinking about flatland, about beings unaware of a higher dimension all around them. And he wondered, what if we are like that?
What if there's a fifth dimension we're oblivious to?
So he took Einstein's theory of gravity, general relativity, which uses four dimensions, three space plus one time.
And just added a fifth dimension to the map.
He did. He worked out the equations for gravity in five dimensions, and something amazing happened. The equations naturally split. Part of them looked exactly like Einstein's 4D gravity equations, and the other part looked exactly like Maxwell's equations for electromagnetism.
Oh, way. Seriously.
Seriously, it was hiding in plain sight mathematically. Gravity and electromagnetism seemed to just fall out of 5D gravity, unified.
That is stunning. A potential unification just by adding one dimension. Einstein must have been floored.
He was intrigued, definitely, cautious about the physical reality of it, but deeply impressed by the mathematical elegance.
And then Klein came along and made it quantum and tiny.
Yes, Klein suggested the dimension wasn't big, but curled up, quantum-sized, related to Planck's constant. That made it less physically outrageous. Perhaps you wouldn't see it directly.
A tiny loop everywhere? Still hard to picture.
It is. But this idea, extra dimensions for unification, it didn't stop there.
It evolved.
Oh, yes. Later theories like supergravity and especially superstring theory, they needed more dimensions.
How many more?
String theory initially pointed towards 10 dimensions, 9 space, 1 time. And then M theory, a kind of synthesis, suggested 11.
11 dimensions. Okay, my head is officially spinning now.
Heh. It's a lot to take in. It pushes intuition to the breaking point.
But the goal is still the same, that unified picture.
Always. That's the driving force. To find the underlying simplicity, the interconnectedness of everything, these extra dimensions, bizarre as they sound, emerge from that deep mathematical and physical quest for unity. They aren't just wild guesses. They're consequences of trying to build a complete theory.
So as we kind of drift towards the end of this cosmic bedtime story, we've journeyed from seeing forces as separate characters.
To glimpsing how they might be part of one family, maybe united in hidden rooms, hidden dimensions of reality.
We've touched on ancient philosophical ideas, mind-bending math, and the frontiers of physics.
And through it all, this thread of human curiosity, this need to understand, to see the bigger picture, even if it involves dimensions we can't easily grasp.
It really does stretch the imagination, doesn't it? But it's born from trying to make sense of it all.
Exactly. It's a testament to our desire to follow the logic, follow the mathematics, wherever it leads, even beyond our senses.
It leaves you wondering, maybe Carl Sagan was right, Maybe the universe is richer and more complex than we can possibly perceive directly.
Maybe those stars are just the visible highlights on an unimaginably vast, multidimensional canvas.
And the search goes on. The quest to read the full story, written in the language of mathematics and woven through the fabric of space-time, maybe even through dimensions unseen.
So, as you drift off tonight, perhaps consider that the universe isn't just expanding outwards. Maybe it's also unfolding, dimension by dimension, in ways we're only just beginning to dream about.